Welcome to Lecture 31, in which we will begin to talk about quantum parallelism and some related ideas. And the first observation I want to make is the following. And you might have already come to this conclusion from your work on the questions at the end of Lecture 30 and in class on Test 30. And the observation is simply this: the Deutsch problem algorithm will not allow one to determine with certainty whether f is constant or non-constant in only one query to u sub f if the input to u sub f is plus 0, minus 0, plus 1, or minus 1. The reason for this, the reason that it works when the input is plus minus, but not when the input is plus 0, minus 0, plus 1, or minus 1, is that plus minus is a superposition of all four of the elements of the standard basis while plus 0, let's say while each of plus 0, minus 0, plus 1, and minus 1 is a superposition of only two of these. And then I want to also add in parentheses, note that is not the case that any input that is the superposition of all four will work. For instance, plus plus doesn't work. So for the Deutsch problem algorithm to work, we need an input to u sub f that is the superposition of all four of the standard basis elements, but that is a necessary condition for it to work with certainty in just one query, but it is not a sufficient condition, because as say here, if you will check the Deutsch problem algorithm, and instead of having plus minus, if you had plus plus, now plus plus is indeed a superposition of all four of the elements in the standard basis. However, if this was the input to u sub f, you still, using the Deutsch problem algorithm, would not be able to determine in just one query whether f was constant or non-constant. But we saw that for plus minus you could. And so again, I want to say that the fact that plus minus is a superposition of all four, that is necessary, but it's not sufficient. Okay, but the very interesting point here is that we have u sub f. We only have one query by u sub f, or one query of u sub f, and we query it. The input is just that one state plus minus. But in effect, what we're doing is we are looking at the action of f on four different things, because that plus minus is the superposition of four different elements in that standard basis. And so this is the idea of quantum parallelism, and this is the idea, this is where we're getting some of our superior performance to the classical algorithm, because we just don't have anything like superposition that holds in the classical case, but in the quantum case, we saw that we did. So that's the first note that we want to make about quantum parallelism, and now let's look at some related ideas. We have been looking at several unitary transformations that act in the following way. We have, let's say, we have seen several unitary transformations that work as follows. We have UF acting on X, Y is equal to X, and then Y exclusive or f of X for some function f. Now, it's important to note here that this X, in the cases that we have seen, X could be a single qubit or it could be multiple qubits. But Y here is a single qubit. Now, just to make sure you follow what I'm talking about, I'm looking at something, for instance, like this. So we'll say, for example. And let's turn to our most commonly used example, the Toffoli gate. So let's say that we have something like this. Okay, now I realize that usually we have called these bits X, Y, and Z, but we can call them anything we wish. And so let's call the qubits here, let's say we have X1, X2, X3, X4, and then down here we will have Y. And so, as an example, if perhaps we had this, then we know that the output over here on the right would be X1, X2, X3, X4, and then this last one would be Y exclusive OR X1 ANDed with X3. So you can see here that in this example, X, so in this case, the notation X actually refers to a qubit, it refers to a state with 4 qubits, X1, X2, X3, X4. But of course, Y just has the 1 qubit, so we could say, maybe let's do it like this. Either 0 or 1. So again now, X is possibly, X could be a single qubit. We've seen examples like that. Or X could have multiple qubits, but the thought is that Y is a single qubit, and it will be either 0 or 1. And we've seen a number of cases like this. Now, continuing, let's have another observation here. When we apply the Hadamard transformation, to the 0 state, we know that we get 1 over square root of 2, 0, plus 1 over square root of 2, 1. In other words, we're operating on just a single element of the standard basis for 1 qubit states, but we obtain an answer that is a superposition of all of the elements in the basis, in the standard basis for 1 qubit states. Now, what about H operating on 0, 0. Well, I think that all of you will remember that this is 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 plus 1/2 1, 1. So the pattern is still holding. When we operate with the Walsh-Hadamard transformation on a single element of the standard basis for 2 qubit states, the result is a superposition of all the elements of the standard basis for 2 qubit states. And let's do one more. Let's say H of 0, 0, 0. And with a little bit of patience, you would see that this will end up being 1 over the square root of 8, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And so, still again in this case, and in fact in every case, what we find is that H, operating on this all zero state, the Walsh-Hadamard transform. Now keep in mind what we're talking about. Now let me make sure this is clear. When I say H operating on 0, that's clear. But here, actually, what I should say is H tensor H, so that you understand that we're going to apply H to the first qubit and also H to the second qubit. And similarly down here, we'll have H, H, and H. So we're going to apply the Walsh-Hadamard transformation in this case to each of the 3 qubits. And in the general case, we could write it as H to the n, and then 0, 0, dot, 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 0, where it's understood that there are n zeros. But in each case, we're inputting just a single element of the standard basis, and we are obtaining a superposition of all the elements of the standard basis. And so the idea then is that so this is how we're going to prepare with this idea of quantum parallelism. If we want to query a unitary transformation, this is often what we will do, is we will prepare this superposition of all the states and then let that be the input, or something similar to that will be the input to the unitary transformation, and then our output will contain some information about everything that is the action of that function on all possible inputs, if we are only clever enough then to be able to extract that information. So that is the idea of quantum parallelism. Still another issue I'd like to briefly discuss here. All of this is getting us ready for our next topic to be addressed in lecture 32. But let's look again here at H. Let's look at this example, H, tensor H, acting on 0, 0. We have already observed that that's equal to 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 plus 1/2 1, 1. Now, the first thing I want to recall for you is the following. Okay, obviously, well, in fact, let me just write it over here. This is obviously we could factor out the 1/2 and then get 0, 0, 0, 1, 1, 0, 1, 1. But you might remember we have not used it much in this course, but in very early in the course, if you were following along in the text, you might remember the following notation. Instead of writing out these 2 qubit states in this way as 0, 0, 0, 1, 1, 0, and 1, 1, the book in the early chapters, I don't recall exactly which chapter, but in some of the early chapters, the book introduced this notation. We would just have 0, 1, 2, and 3. And the idea here is that 0, 0 is the 2-bit representation of the decimal number 0. 0, 1 is the representation of 1. 1, 0 is 2. And 1, 1 is 3. Obviously, you have to be careful in using this notation. When you use this notation, it's important to know how many bits you're talking about, because otherwise, how do you distinguish this 0 from the single qubit state 0 that we have here? You can't. So it's important to know when you use this notation exactly how many qubits there are in the problem that you're talking about. But it is definitely going to be worthwhile in our next few discussions to understand this notation. And so continuing with this, then what we can say is that H2 acting on 0, 0 is equal to 1 over the square root of 2 squared times the sum from x equals 0 to 2 squared minus 1 of x. Now that you can clearly see that this is correct, because 2 squared, of course, is 4, and the square root of 4 is 2, so this would give us a 1/2 out here, which matches this 1/2, and then this sum would run from 0 up to 4 minus 1 is 3, so we would get 0 and 1 and 2 and 3, which we have here. So you might wonder why we're writing it in this more complicated form, but the answer is the following, because once you you see this as an example of the more general case, which is this Hn acting on the n qubit state that consists of all zeros is equal to 1 over the square root of 2 to the nth power times the sum x equals 0 to 2 to the n minus 1 of x. Or we might also write 1 over the square root of capital N sum x equal 0 to n minus 1 of x, where n, capital N, equals 2 raised to the lowercase n power. This piece of information here, describing the effect of applying the Walsh-Hadamard transform to the n-qubit state that consists of all zeros. This piece of information is important, and it's something that we will be using repeatedly in the very near future. So it's make sure you understand this. Also, be aware that your book will write this same equation in the following form. Instead of having h to the n, they'll just use w for Walsh, and they will just write that state of all zeros as 1 0. But again, you need to understand that that is the n-qubit zero state. Okay, so this is how your book writes that in a nice condensed notation. Now, in everything that we've been discussing in the past few moments, we've had w or h to the n acting on the zero state. But we might ask ourselves, how does w act on other states? To answer this question, let's consider 2-qubit states. Okay, so we already know that w, and by the way, what we're doing here is we want to construct the w matrix. So w acting on 0, 0, we have already learned will be 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 plus 1/2 1, 1. So that means that we're going to be taking the basis now, the standard basis in the standard order. And so, and of course, 0, 0 then, if we're using the standard order, 0, 0 is the first element of the standard basis, and therefore these terms constitute the first column of the matrix of W. So that first column will be all 1/2s. Now, what about W acting on 0, 1? Well, let's see what we'll get in this case. This is 1 over the square root of 2. When we have W acting on 0, we will get 0 plus 1. And then from okay, I'm sorry, let me rephrase that. Remember that the W, this Walsh transform, or Hadamard-Walsh transform, is really just the idea that H is acting on each individual qubit. So when H acts on that first qubit of 0, we'll get 1 over square root of 2, 0 plus 1. And then when we have the H also acting on the second qubit, which is 1, and so that one will give us 0 minus 1. And therefore, when we multiply this out, we get 1/2 from the 1 over square root of 2 times 1 over square root of 2. And we'll get 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. So the second column of the W matrix would be plus 1/2, minus 1/2, plus 1/2, minus 1/2. Now let's look at W acting on 1, 0. Okay, the Hadamard transformation will act on that first one to give us 1 over square root of 2. And since the first qubit is 1, we will get 0 minus 1. And when we also have another Hadamard gate or Hadamard transformation acting on that second qubit, we get 1 over square root of 2. And since the second qubit is 0, then we will get 0 plus 1. And so when we multiply this one out, we get 1/2 0, 0 plus 0, 1 minus 1, 0 minus 1, 1. And finally, W acting on 1, 1 will give us 1 over square root of 2, 0 minus 1, 1 over square root of 2, 0 minus 1, and so we get 1/2 of 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. So when we put this all together, we see that the matrix for the Walsh transformation in the 2 qubit situation will be 1/2, 1/2, 1/2, 1/2. This is 2 qubits, 2 qubit states. Okay, 1/2, 1/2, 1/2, 1/2 is the first column. The second column will be 1/2, and then minus 1/2, and plus 1/2, and minus 1/2. The third column, the first 2 entries will be positive 1/2, and the third and fourth entries will be negative 1/2. And then for the last column of W, the first and last entries will be positive 1/2. The second and third entries will be negative 1/2. So we get 1/2, negative 1/2, negative 1/2, and 1/2. Now recall that we use the notation WRS equals the term in the rth row and sth column of W. Okay, that's just the way that people denote the terms in a matrix. And so now we observe that in this case, and by this case I mean 2 qubit states, we have WRS is equal to 1 over the square root of 2 to the nth power, 2 to the squared. 1 over the square root of 2 squared times negative 1 to the R times S power. Now, let's check this out and make sure. Make sure it makes sense. Well, first of all, 2 squared is 4, and of course the square root of 4 is 2, so that would be a 1/2 out here. So I'm sure you'll agree that 1/2 is the magnitude of all these terms. But does this correctly predict all of the signs in it? Okay, well, in the first case here, we have, well, wait just a second. Okay, now to apply this, we need to understand what we're talking about with R and S. Okay, so for the R and S that are down here, we can think about these just as you usually would. What I mean by that is you can say, like if you wanted to figure out the third row and the fourth column, then you can just use R equals 3 and S equals 4. But to figure out the value of this R times S, it's not 3 times 4, which would give you 12. Instead, what you need to do is the following. First of all, you need to know the number of qubits that you have, which in this case will be 2. And then R and S will be written as follows. Okay, sorry, I'm going to have to make a small modification of what we just said. Let's, of the usual way to number the rows and the columns of a matrix is as follows. This would be the first row of W, this would be the second row of W, this would be the third row, and this would be the fourth row. Likewise, this is the first column of W, this is the second column, here is the third column, and here's the fourth column. That's the conventional way to number the rows and columns of a matrix. However, we now will number the rows as this is the 0th row, first row, second row, and third row. So in numbering the rows, we start with 0, and likewise in numbering the columns, we will start with 0. So this will be the 0th column, first column, second column, and third column. Okay, so now that that's clear, and we can still leave this remark here. Recall that WRS is the term in the rth row and S column of W, and I'll just put a note over here so we don't forget. We'll say R and S both range from 0 to 2 to the n minus 1, where n is the number of qubits. So in this particular case, with 2 qubits, n will be 2, so we have 2 squared, which is 4 minus 1, or 3. So R and S in this case are ranging from 0 to 3. So again, here's your 0th row, first row, second row, third row, 0th column, first column, second column, third column. So all of this is the same. And now down here, this will also remain the same now, but we're ready to interpret it. So as I mentioned a moment ago, if we wanted to know, let's say this element right here, okay? If we wanted to use the formula to predict this element right here, well, this is in the second, this is in row number 2, again, 0, 1, 2. So this would be in row 2 and in column 1, because this is column 0 and this is column 1. So this would be the W21. Now, how do we evaluate R dot S? Well, what we need to do, okay, to evaluate R dot S, write R and S both as binary, actually we can say as n-bit binary numbers, then R dot S is equal to the number of bit positions in which both R and S have ones. So again, if we were looking at this term right here, this is the 2-1 term. So we'll say, for example, W21 is equal to 1 over, and the square root of 2 squared is 2. And now we would have -1, and now we want to figure out R dot S. Okay, R is equal to 2, and we need to write 2 as a 2-bit binary number, and of course that's easy. So R would be 1, 0. S is equal to 1. How do we write 1 as a 2-bit binary number? Well, that's easy also. That's equal to 0, 1. And now, what is the number of bit positions in which both R and S have ones? Well, it's 0, because the 1 in R occurs in the first bit, but S has a 0 in that bit, and then the 1 in S occurs in the second bit, but R has a 0 in that bit. So neither one of these numbers has a 1, or they don't have ones in the common positions, and therefore R dot S in this case is equal to 0. And so we fill in 0 here, and of course -1 to the 0 power is 1, and so we get 1/2 for W21, and in fact that is the correct answer. Now let's do another example to make sure that we understand the application of this formula. Let's maybe try to predict this. Let's try to calculate this term right here. Okay, this is the term in row number. Again, let me actually circle it just so you'll know for sure. Okay, now let's calculate this one. Okay, actually you try to do that yourselves first. I encourage you, because I think this is not too hard a concept. Try to calculate that first yourselves using this formula, and then we'll all do it together. Okay, so how would this go? Again, this is row 0, row 1 here. So we have row number R is 1, and what is the column number? Well, remember column 0, 1, 2, 3, so this is column number 3. So we're calculating W13, and according to this formula right here, again, the square root of 1 to the square root of 2 to the second power is 2. So we have 1/2. And now -1 to the R dot S power, and let's find out what R and S are here. Now R is equal to 1. And 1 written as a 2-bit binary number is 0, 1. S is 3. And the 3 written as a 2-bit binary number is 1, 1. And now how many positions do they both have a 1? In one position. In this position they both have a 1. They do not both have a 1 in this position. And therefore R dot S in this case is equal to 1. And therefore we put 1 up here, and we get -1/2 for W13, which indeed is consistent with what we have calculated up here. So, and I'll leave it to you to verify that this formula is correct for all of these. And in fact, the formula for W is general. That is, in the case of n qubit states, WRS is equal to 1 over the square root of 2 to the n negative 1 to the R dot S power, where R where we need to remember to write R and S as n-bit binary numbers, and R dot S will be the number of bit positions in which both have ones. And also remember, I'll say also note that 0 is less than or equal to R is less than or equal to 2 to the n minus 1, which is consistent with the fact that R can be written as an n-bit binary number, because the largest number that can be expressed as an n-bit binary number is 2 to the n minus 1. And of course, the same is true for S. So that is still another observation that will be helpful to us in upcoming lectures. And I think that I'll stop at that point and come up now with a problem. Okay, so since we started off this lecture talking about the Deutsch problem algorithm, I'd like to ask these first two problems about that algorithm, and then in the in-lecture part we'll cover something about the Walsh-Hadamard transformation, or this quantum parallelism. And of course it won't be anything too challenging, just to make sure that you're understanding this introductory material. But now for the questions, the two lecture problems. This is similar to what we've done before, with one exception. You remember at the beginning of this lecture we said that it was the reason that the plus minus input would work while plus 0, minus 0, plus 1, and minus 1 did not work, is that plus minus is a superposition of all four elements of the standard basis, whereas each of these is a superposition of just two. Now we also observed that that's not quite enough. Just the fact that it's a superposition of all four doesn't guarantee that it will work, because plus plus is also a superposition of all four, but it doesn't work either. So the questions, these first two questions, regard another possibility, another state that is a superposition of all four, and that is minus plus. And so the question here is simply, if minus plus is the input to the unitary transformation, and then we apply h to the first qubit of the result, then would this work? Would the if you apply the Deutsch, if well, if you then measure the first qubit with the standard basis. So in other words, if you apply the Deutsch problem algorithm, everything is just the same as what we discussed in the last lecture, except the input to the unitary transformation use of f is minus plus instead of plus minus. Will it now give you a certain indication of whether f is constant or non-constant? And so the question is this: in the first case, if f is a constant function, will it give you plus with certainty, minus with certainty, 0 with certainty, 1 with certainty, or possibly 0 and possibly 1? And likewise, if f of 0, if f is a non-constant function, will it give you a plus with certainty, minus with certainty, 0 with certainty, 1 with certainty, or possibly 0 and possibly 1? And keep in mind that the Deutsch problem algorithm is, it only really works if the answers to these two problems here are different. The answers have to be different, and neither answer can be E. If either answer is E, then that means it doesn't work in just one query. So you don't want either answer, and that's why the cases, these other cases we've been looking at, don't work, because we found some E answers before. But now I'm going to ask again in this case. I mean, you don't have to answer that separate question; just answer these two questions. But overall, I can tell you that for the algorithm to work in just one query, you have to have different answers for these two, and furthermore, neither answer can be E. So that's it for the lecture questions, and again for the in-class question of this, I would expect that you should be ready for something along these lines. But make sure you understand the other material here as well. And that will conclude lecture 31. So good luck.